Okay, this section is on properties of functions. We're going to look at a number of different um, properties that functions can have. Okay, now the first thing we want to talk about is finding the domain. Now I know we did that in the last section with a graph, but this time we're going to get it from an equation. For example, let's find the domain of f of x equals root x plus 3. Okay, now what we know about radicals, or things underneath the radical sign, is that they cannot be negative, right? It's because you can't take the square root of a negative number. So that limits the domain, okay? The values, or the thing under the radical sign has to be greater than or equal to 0. It can't be negative. So we just take whatever's under the radical sign, x plus 3, and we set it equal to greater than or equal to 0. Okay, we say that that is greater than or equal to 0. And then by doing a little basic algebra, by subtracting 3 from both sides, we can see then that the domain is restricted to values of x that's greater than or equal to negative 3. Okay? That's an inequality notation. If we wrote it in interval notation, it would be like that. Okay? So we have a restricted domain here. Okay? This can only have values. The function only has values for x is greater than or equal to negative 3. All right, what about this one? Now, because of the radical, we know that x cannot be negative, right? Okay, it could be 0, but it can't be negative. All right. Now, because of the denominator, we also know that it cannot be 7, because if it were, then we would have a denominator of 0, and that just doesn't exist. So we have two conditions for x. It can't be negative, and it also cannot be 7. Okay. So we can write it like this. The domain x must be greater than or equal to 0 because of the numerator here, but that excludes the value 7 because that would make the denominator 0. Okay, so we can write it like that. Or in interval notation, we can write it like that. So domains are restricted by if it's a square root, the square roots can't be negative, and the denominators can't be 0. Those are the things that you have to look for when seeing what restrictions the domains have. What about this one? Okay, now we have a square root in the denominator. Okay, so we know that 4a minus 8 can't be negative, but it also cannot be 0, because that would make square root of 0 0, that would make the denominator 0. So now we have to say that 4a minus 8 is greater than 0. It cannot include 0, like it did up in this example. It's non-inclusive with 0. So 4a minus 8 is greater than 0. Okay, and that actually covers both bases. It can't be negative, nor can it be 0. Okay, add 8 to both sides, and you get 4 is equal to 8, and then divide each side by 4, and you get a is greater than or equal to 2. Oh, sorry, a is greater than 2. So the domain then is a is greater than 2, or writing it in interval notation, we can write it like that. And that's the domain of that. Okay. Okay, the second property we want to talk about is discontinuity. Okay, and I'm going to use this piecewise function as an example. There are 3 types of discontinuities. One is called a hole. Okay, and the hole an example of a hole is right here. Okay, there's simply a value at x equals 3. This function doesn't have a value, so we call that a hole. Okay, and we can classify discontinuities as either removable or non-removable. Okay, and the way to tell whether a discontinuity is removable is if you can take your pencil and just go right past it without having to pick up your pencil. You can just blow right through it. And so this hole is what we call a removable discontinuity. Okay? Okay, the second kind of discontinuity is a jump discontinuity. And an example of a jump discontinuity is right here. Okay? Now, if we were drawing this function starting from the negative, I would get to here, and I'd have to pick up my pencil in order to get to the other part of the function. When you have to pick up your pencil to overcome the jump, all right, then that is a non-removable discontinuity. Okay, so with the hole, it's removable because I can just blow right past with my pencil. But for the jump one, I actually have to pick it up and bring it over here and continue. Okay, so that's a non-removable one. The third type of discontinuity is what we call infinite, and that's when you have an asymptote. And although it isn't written in here, there's an asymptote right here. Okay, and when there's an asymptote, the function on both sides goes to infinity, right? So they call that an infinite discontinuity. And once again, it is non-removable because I would have to pick up my pencil to get to the other part of the function. Okay, so the three types of discontinuity: a hole, which looks like that, a jump, which looks like that, and then an infinite one involves an asymptote. Okay? All right, now let's do this. Find and classify the discontinuities of f of x equals quantity x minus 5 over quantity x plus 1. Now we're not going to have a graph to help us out. We just have to use the function. Okay, well, what do we know? Well, we know that the denominator can't be 0. So we know that x plus 1 cannot be 0. Okay, and then so we're set it equal like that, and then subtract 1 from each side, and we have x is equal cannot equal negative 1. So we know that the discontinuity there is there's a discontinuity at x equals negative 1. Okay, now we're going to cheat a little bit and actually use a graph to classify it. Later on, we'll be able to figure out how to do it without a graph, but here's the graph of it. If you graphed in Desmos, there is actually an asymptote right there at x equals negative 1. And with experience, you'll recognize that if that asymptotes occur at values of x that make the denominator 0. Okay, so there's an asymptote at x equals negative 1. So we can classify this as infinite and non-removable. Okay, now let's classify this one. Find and classify these discontinuities of this. Okay, now what we have to do is factor this denominator. Okay, and when we factor it, we get this: quantity x plus 5 times quantity x plus 1. Okay, now we know the denominator cannot be 0. Okay, and similar to the zero product property rule, so we know that that cannot be 0, so that the first one can't be 0 or the second one can't be 0, right? Solving for the first one, we get x cannot equal negative 5. And for the second one, x cannot equal negative 1. So we know we have discontinuities at x equals negative 1 and x equals negative 5. Now, how do we classify them without using a graph? Okay, here's what you do. You go back to here, and here's the rule. If the factor can be canceled out, it's a whole. Okay, and notice that x plus 1 can be canceled out. Okay, so that makes the discontinuity at x equals negative 1, that makes it a whole. Okay, so if you can cancel out the factors, then it's a whole, and therefore removable. If you cannot cancel the factor out, it's an infinite discontinuity because there's an asymptote, and that will be for x plus 5. X plus 5 cannot be canceled out, and therefore that makes that discontinuity an infinite discontinuity. Okay, and just for fun, let's graph this. So I graph this function, and it looks like this in Desmos. Desmos doesn't actually put the hole in there. I put that in there myself. But you can see the asymptote, okay? And then there's actually a hole in there. I don't know if we zoomed all the way in. I don't even know what it would do there. Never even thought to try that. I wonder what would happen if we zoomed all the way in to that value, because eventually there's a hole there, right? I don't know that Desmos can do that. Maybe I'll try that later. So here there's an asymptote at x equals negative 5. Okay, the next property that we can talk about is extrema. Okay, and the easiest way to do this is with an example. So use a graph to find the local extrema of this function. Okay, now we're going to use a graph, so we're going to graph this in Desmos. I invite you to pause this right now and open a Desmos tab and graph this function, see what it looks like, and then sketch it out in your packet. So just sketch it on that grid. Okay, well here's what I came up with. Here's what Desmos gave me. All right, and now we can see if we talk about local maximums and local minimums, maxima or minima, there's a local maximum right here. Okay? And then there's a local minimum right there and right there. Okay? And that's how you find the extrema. You simply graph it and then look at where, you know, it momentarily peaks and momentarily dips. All right? There's also something called absolute maximum, which actually would be infinity here, and absolute minimum. But we don't have to worry about that right now. Just local maximum, local minimum. And you can get that by inspection. And so I'm going to say that the local maximum is around, I don't know, 0.3-ish. And then there's a local minimum there at, I don't know, negative 2.2. And then this one I called at 2. Answers might slightly vary there, but we should all be in the same ballpark to find the local maximum and local minimum. So we can simply find those with a graph, and that's how to find extrema. Okay. Okay, one other thing, last thing we're going to talk about is symmetry. Okay, now we can classify functions as either even functions or odd functions. Okay, let's talk about even functions first. Even functions are symmetric with the y-axis. Okay, now as an example of an even function, let's look at this and let's graph this. And if you graph this in Desmos, it looks like this. Okay, and then the y-axis is an axis of symmetry. That is, the y-axis is a mirror. It looks the same on both sides. Okay, and this is a property of an even function. The y-axis is an axis of symmetry, and the function is a mirror image of each other, of itself, on each side of that axis of symmetry. Other examples of even functions. There's one. Note, again, the y-axis is an axis of symmetry, mirror image on each side. There's another one. And there's another one. Okay. In each case, the y-axis is an axis of symmetry. All right, now here's a property of even functions. For even functions, f of negative x is the same as f of x. Okay, now let's show that with our first example of an even function that we had a couple slides ago. What we're going to do is we're going to plug in negative x for x and see if it equals the original function. So f of negative x will be negative x squared minus 3. But negative x squared is the same as x squared. And note that it matches up. Okay, so f of negative x is the same as f of x, and that makes this an even function. All right, I'd like you to pause and see if and verify that this is an even function by finding f of negative x. Plug negative x into there. So pause and then come back. All right, let's see here. F of negative x would be square root of negative x squared plus 2. And once again, for the same thing as above, top of the slide, negative x squared is the same as x squared, so we get f of negative x being the same as f of x, and that makes it an even function. Okay, and just for fun, I plotted this in Desmos, and yes, indeed, the y-axis is an axis of symmetry. Okay, so that's an even function. Okay, now odd functions. Odd functions are symmetric with the origin. And an example of an odd function would be this, f of x equals x cubed minus 3x. And if you plotted this in Desmos, it would look like this. Now this is symmetric with the origin. So note that if I go up to there, okay, and I take that, if I mirror 2, 2, if I mirror that with the origin, I get negative 2, negative 2. And so that mirrors with the origin, as well as these points, every other point. So this is an example of an odd function. The origin is the point of symmetry. There's no real axis of symmetry. There's a point of symmetry, okay, in this case. And this would be the origin. Other examples of odd functions here. Okay. There. Symmetric with the origin. And here. Okay, symmetric with the origin. Okay. Okay, those are other examples of odd functions. For odd functions, the property is f of negative x is equal to negative f of x. Okay, now let's show that with the original example we did a couple slides ago, the example I used of an odd function, which as you recall looked like this. Okay, so I'm going to find f of negative x by inserting negative x in for x and analyzing. Okay, negative x cubed is negative x times negative x times negative x, which is negative x cubed. And then negative 3 times negative x is positive 3x. Okay. Now, what I'm going to do is I'm going to factor out a negative 1 from each term. Okay, and then what we're going to get is this, which if you distribute that negative 1 back through, you'll see that you end up with this, so that works. Okay, but notice that x cubed minus 3x is the original function. So f of negative x is equal to negative f of x. And that satisfies the property of odd functions, right? Okay. One more example to do, and that is to verify that this is an odd function. So let's find f of negative x, okay? And so we do that, all right? At this point, see if, how about pause this video and see if you can show that this value that this function satisfies the condition of an odd function. All right, so the numerator is going to become negative 3x. The denominator, negative x squared, is positive x squared, right? Negative times negative. And so we get this. I'm going to pull the negative sign out to write it like this. And then notice that 3x over quantity x squared plus 1 is the original function. So this is negative f of x. So the function is odd. And just to show that graphically, you plot this in Desmos, and here's what it looks like. And that, as you can see, it's symmetric with the origin. So it shows that that's an odd function. Yeah. Okay, so we talked in this section about domains and ranges and finding them from the function instead of a graph. Okay, and we talked about discontinuities, the different types, and how you can classify them from the equation. Then we talked about extrema, which you can find from a graph. And then we talked about symmetry in terms of even and odd functions. So, time to practice these skills that we've learned in this section with the practice problem.